Hey everyone, welcome back to the dining room shop. Quick little update today on the roundness tester I mentioned in one of the previous spindle videos, and just getting higher resolutions out of your electronic indicator using some additional electronics. I think I mentioned it, but this is the roundness tester I made. It's, there's not much going on here. It's an air bearing spindle from Professional Instruments, and on the bottom of it there's an encoder. So we can track the position, and you have an indicator on your part up here, and you can measure the roundness as it spins around and use the encoder to keep track of position. And I talk about all this in the spindle metrology stuff. Anyways, the way I was doing it before is with this combination of chips here. I just had an Arduino Nano reading the encoder position, and then I needed a way to digitize the signal from my indicator. This has an analog output, plus or minus 1 volt, which represents the full scale on the front panel here. And I needed a way to get that into the computer. So we use this ADS8681 this is a little breakout board for it from Adafruit. I think it's a TI chip. It's multi-channel, 16-bit, which is good. But the annoying part about this is this only gives me, I think the maximum sampling rate was 800 and something hertz, not even 1 kilohertz. I thought that would be fine when I bought it, but I found out very quickly when trying to use the roundness tester, if I spun it, at any reasonable speed, this could not sample fast enough, and it would actually miss data points, and then that would kind of screw all of the further post-processing downstream. So not fast enough. It was usable, but you basically had to spin the thing at maybe 1 revolution every 20 seconds or so. It's just unfeasibly slow. So this is the upgraded setup here. Don't mind this interface. This is just me scavenging the analog output from this other crappy breakout board I had for that stuff. None of this is very polished or finalized yet. Anyway, this is the new ADC, the ADS8681, also from TI. Single channel, still 16 bits, but 1 mega sample per second. So quite the upgrade there. Also upgraded the microcontroller I'm using. Now we've got a Teensy 4.1, which 16 megahertz clock speed, 600 megahertz clock speed. So this is now blazingly fast. If I want to record locally on the Teensy, I can literally do that at just about 1 million samples per second. But the way the software works is I stream the data live back to the computer and record it there. And even still, I can do that at about 500 kilosamples per second. So really, speed is no longer an issue. It's completely, that problem is completely solved. I gotta say, this chip was a little annoying to work with. This communicates over I2C, and it's got a nice library for it and everything. When you're writing your C++ code, you just, call the ADC read function and it does everything for you. And there's an ADC configuration function. Super nice for the electronically disinclined like myself. This, on the other hand, not so nice. Communicates via SPI, and there is no library. And so it took me a couple days of slogging through the data sheet to figure out exactly what combinations of 1s and 0s to send this thing in the right order to configure it so it's reading in the right voltage range, because there's multiple ranges, and then read it back. It's not, maybe easy for some people, but not difficult, or not easy for myself. Anyway, if you do want to use one of these chips, there's these breakout boards are readily available on, I got this off AliExpress for like 25 bucks. But if you get one and you want basically a pseudo library to help you use it, shoot me an email and I can give you the code that I wrote to talk to it a little easier. anyways, let's look at the results here. So we're on the finest range in metric on this, on my Tessa here. So we're looking at the top scale, and it's in microns, so plus or minus 3 microns. The small ticks are then 0.1 micron per division, so pretty fine. Do not judge my indicator setup here. I'm severely lacking in metrology resources with this current setup, but you get the idea. I've just got this adjustment stage and it's measuring the displacement there. So this is actually a pretty stiff setup, so I don't have any fun demos of, you know, me tapping on the table or jumping around on the floor or anything like that. But, you know, I can show you here, if I push my finger on it, you know, we get a displacement there just for me dragging my finger. But that's pretty close to the minimum resolution of the readout there. So I've got this streaming to, this is just looking at the raw serial output from Arduino here. There we go. And so sorry for the unit change, but this scale is in inches. So the two lines here, this is the top and bottom of the scale. This is 5 microinches. So plus 5 microinches, 0, minus 5 microinches. For metric friends there, if we look at this 4 here, this is plus or minus 0.1 micron. So this distance here is equivalent to 1 tick on the top scale there, for context. So you can see what I was concerned about with, you know, trying to get these super high resolutions is, you know, I didn't know how good the noise floor, the electrical noise floor of the analog output was. But I'm pretty pleased with these results here. So it looks like the noise is, you know, down on the order of, I mean, it's certainly less than 1/4 of a microinch. I think it's probably around 5 nanometers or something like that. I'm pretty pleased with it. And here I can do the same thing, drag my finger on it as before, and you can see some output there. It is actually surprisingly stiff. Like I'm have to push on this a decent amount just to get it to deflect the 5 microinches that we have on our scale there. But, you know, you could keep zooming in on this and really, you know, get a much higher resolution than what you could with the just the raw scale on the amplifier there. And the other benefit is, because this thing is so fast and I can take so many samples so quickly, I can also do some averaging and basically reduce that electrical noise floor even further if I want to. Honestly, I'm not going to do that. This is more than enough for what I'm trying to do here. But yeah, this is the new electrical setup. I need to integrate that code into the actual roundness tester code, and then pretty soon I'll do a full update video, or not update video, but I guess project summary video on the roundness tester, and we'll show it working and how the actual MATLAB software works. So yeah, that's pretty much it. Thanks for watching.